Here in number 3, we have another initial condition, y of 0 equals 3. So let's solve this differential equation. Now remember, y prime is the same as dy dx. And we can isolate dy dx by moving xy to the other side. Now that we have dy dx on its own, we need to separate variables. But since both terms on the right have y, I'm going to factor that out as a GCF. So now we have terms with only y and terms with x. So now we will separate those variables. In order to get y on one side, we have dy over y equals 1 minus x dx. Now that we've separated variables, we take antiderivatives. The antiderivative of dy over y is ln absolute value of y plus c1. That equals the antiderivative of the right side, x minus x squared over 2 plus c2. Now we will consolidate our constants of antidifferentiation. Ln absolute value of y is x minus x squared over 2 plus c3. Now we will use this initial condition to solve for our constant of antidifferentiation. When x is 0, y is 3. So we have ln absolute value of 3 equals 0 minus 0 squared over 2 plus c3. So that makes c3 equal to ln absolute value of 3. Now we can plug this back in to our solved differential equation. Ln absolute value of y equals x minus x squared over 2 plus ln absolute value of 3. In order to solve for y, I'm going to exponentiate each side. So we know e to the ln cancels and just leaves y. Now remember, properties of exponents states when you are adding your exponents, so let's say since we're adding this exponent, that really means that we are multiplying powers with the same base. So that's really e to the x minus x squared over 2 times e to the ln absolute value of 3. So that's working properties of exponents backwards. So now this e to the ln cancels, and we have y equals 3 e to the x minus x squared over 2. So remember, we always solve for c before we solve for y.